Okay, we've got 44 slides, and we have approximately 44 minutes. Think we can do it? How many of you have ever been to an auction before? Okay, that one was easy. Now in this case, what we're going to do is we're going to give you some problems which test your ability to correlate porosity and permeability. Only a fraction of you, and I use that word correctly, had me for petrophysics. The rest of you had someone else. And what I want to do is see how well you can establish a relationship between variables that shouldn't establish relationships. Again, Mr. Stone, we come back to you. You don't get it? Mm-hmm. Yes, some things shouldn't establish relationships. Just trying to help. He hates me. Where's Mr. Cottle today? Oh, you're laughing. Nice. You're next. Okay. Now, for somebody who's had a geology class before, which is, I assume, most of you, I want you to explain to your grandmother that these mountains are all igneous, or, well, they could be volcanic, and, you know, stuff came out of them, and then somehow they got weathered over millions and billions of years, and they became sedimentary rocks. And in some cases, this process has gone on over and over again, so it's intruded, or it's, you know, somehow the mountains are formed. But we're going to start with this point. We're going to start with the mountain range being a source of materials. And that mountain range is weathered, and those materials break off, and they go down by melt off and that sort of things into what's called an alluvial valley. And then gradually this river becomes wider and more sinuous. And why is it wider and more sinuous? Because it slows down. Okay, and it's carrying a sediment load, and it deposits things wherever the velocity is insufficient for the particles to be carried. And then if it's a transgressive sequence like this, so delta is prograding out over older sediments, and that material comes out in the ocean. Now you can imagine you're all thinking, well, this is pretty stupid, Tom. Why are you going over this? Because I want you to understand the kinds of reservoirs that you're going to be seeing. Most of the reservoirs that people think about are something like, a barrier island, like Galveston, where it's a couple of miles wide, 20 miles long, and absolutely packed to the gills with beach sand. How many times in your career do you think you're going to see something like that? Not very often. Sometimes you think, you might find a shelf sandstone or a river sandstone, and sometimes you do. But the vast majority of the kinds of reservoirs you're going to see in your career are going to be out here. And what you can imagine is that you can almost project this depositional sequence to right here. They look similar. It's a system that has a transport load. It drops it out. There'll be channels inside of this. These are what is called turbidites. Turbidite. Come on, pen. Okay. And turbidites come from turbidity currents, which are density loads of sediment, and they're deposited. How big are these things? They're gigantic. When you hear about people trying to pursue reservoirs in the Gulf of Mexico in 10,000 feet of water, what kind of rocks are those? They're turbidites. And turbidites can be extremely low permeability. They can be essentially shale. In some cases they are. Or they can even have parts of them which are extremely high permeability, as much as half a Darcy permeability in some of these channel deposits. And this fellow Berg, and I think there's a copy of his book in the Petty 324 materials, he went as far as to characterize each depositional sequence with a sand grain size. This is size, and then this is content or material, and he shows how they look. And I know you're going, this is something for geologists to do, but you're going to have to be the interface between geologists and yourselves, and you know, you have to at least know the words they're using. Does anyone surprised that a fluvial channel and a turbidity current look very similar? That is, this and this look very similar. Here's the pattern here. Here's the pattern here. Here's the pattern here. Here's a pattern here. Why is that? I need a volunteer. Yes. Okay. And in this case, it's kind of a coincidence, but we think that these turbidite areas act like a river system. They're not continuous transport. This material that comes off of here may only do so every 100 years or so, but it's a huge block of material that slumps off into the basin. Okay, so that's something that could be a possibility. How could you tell the difference between these? How many of you, your parents told you to be a geologist? Anybody? Everybody's like, who's that idiot? So nobody's parents told them to be a geologist? Nobody will admit it. Okay? Well, this is why we have geologists, because they go look at the little bugs and the little critters that live there, and they say, no, that's not a little bug that lives in a river. That's a little bug that lives at the bottom of the ocean. And there's also something else. These traces are not so clean. They're just full of breaks like this, small laminations. And you'll see that quite often. If you ever start to look at well logs for turbidites, they're all jumping around because it's going between sand and shale, sand and shale, sand and shale. And sometimes on a very small scale, sometimes a few centimeters, sometimes a few feet. Okay? Now, let's go to the next slide. I don't want to do that. Okay, give me more. Now this is carbonates, and let's just say the carbonates are all a product of two different things. One is its origin, or its genesis, and two is its diagenesis, what happened to it. Carbonates are generally made out of plant or even skeletal or animal matter that decays in an ocean environment, and it drops, and you know, billions and trillions and quadrillions of them fall on top of each other, and they form these sedimentary layers. They're compressed. Sometimes they don't have very much porosity or permeability, and other times they have enormous porosity and permeability. Can you give me an example of a carbonate system which does not have much porosity or permeability but has a lot of oil in place? Anybody? Anybody from Midland? Yeah? Oh, you don't count. Anybody else from Midland? Okay. Tell us some of the reservoir names out there. Big Chief, Coca-Cola. Come on, David. The San Andreas. Okay. That one's actually a moderate porosity and permeability dolomite. It's pretty good rock. The one that sticks out in my mind is a Clear Fork. It's huge. It's 1,500 feet thick, and it looks about like that tabletop, but there's an awful lot of oil in it. It's produced some. It's got a lot more to produce. Can you name a very high productivity carbonate reservoir? Anyone? Guar, which is the reservoir in Saudi Arabia. What is the gas reservoir, the North Field, as they call it in Qatar, or the South Pars Field, as they call it in Iran? What's that? What kind of rock is that? It's a dolomite. It's fairly good permeability. A lot of things happen when these rocks are transformed. I'm not sure what the origin of it is, but it turns out that that gas is pretty sour. They have to extract sulfur from it. So right now I think Qatar and Iran, and for that matter Kazakhstan, they have huge sulfur extraction facilities for removing, well, in Kazakhstan it's oil, but the other two it's gas. We're talking about porosity and permeability of something, and you can see that what this fella has done is he split it out into different pore scale openings, and as you can imagine, the smaller the pore openings, the lower the permeability. The irony of this is the smaller pore openings, the higher the porosity. At any rate, carbonates, just hold them in your mind. We're not going to test you on it or anything like that. Just wanted you to be aware that they have their own little isms. Now, this fellow by the name of Archie, those of you who had me for Petty 311, we're going to cover everything he did in 10 seconds. Ready? Pore size distribution controls everything. It controls capillary pressure. It controls the fluid interactions and the fluid behavior. Then we have the water saturation and hydrocarbons. We have the electrical resistivity. We have permeability. We have porosity. And then we have different things that can be taken from that. I'm going to erase these for the purpose of identifying some relationships. Archie, 1950, he said the relationship here between saturation and permeability wasn't clear. The relation between permeability and electric logs is not clear. And the relationship even between permeability and porosity is not clear. Wow. So this is a pretty simple cartoon that basically tells you why you're going to have a job. Why are you going to have a job? Because these relationships can be sort of surrounded, but we cannot quantify permeability from remote measurements. We have to actually physically measure it from the rock, or we have to produce the well, which is what this course is all about, estimating permeability from flow. But these relationships are going to make life tough for us. There's never going to be a perfect log or a perfect material that allows us to investigate reservoir properties remotely. I know that's a strong statement. Never is a big word, but I believe you're never going to see a unique characterization of the reservoir from remote measurements. Recently, a company has come out with a device they drag behind a ship, and it has to be in fairly deep water. This device draws electrical current through the earth, and they're able to create an image of the subsurface down to about 3 kilometers. So about 9,000 feet, a little bit more than that. And so what you can see in this image is the sort of a seismic-like interpretation of the reservoir. And these guys, of course, sell it as being able to see saturations, but that's probably not true. What about using seismic to estimate porosity? Does that sound like a good idea? Do you think you're going to be able to do that? You're taking the class before this is Petty 321. When you talk about the sonic log, you're using sonic travel times to estimate porosity. And seismic waves are a type of, not sound, but similar kind of thing. So maybe you can correlate seismic behavior with sonic logs, and that's actually what people do. The most famous, I guess, relationship is that permeability is an exponential function of porosity. How did this come about? Well, people like Archie plotted data, and they put a straight line through it, and they said that was the end of the story. Is that true? No. Correlating porosity and permeability is entirely too simple. It would be like trying to correlate Marmina's behavior based only on Mr. Stone, which could happen, I guess, if you guys were... No, it'll never happen. How's that? We'll leave it at that. So how do we incorporate other variables into this? How do we add porosity, saturation, V-shale, etc.? How do we do all those things? That's why we're going to give you homework on it. So we don't know the answer either. All right. And then we went so far as to start looking at people writing books on the subject, and you can see that this gentleman looked at permeability versus porosity. It's the same thing. It's, again, the exponential trend. And he's drawn a trend here for a limestone, here for a dolomite, here for this, here for that. And these are all given as a trend, but actually there's a cloud of data points around these. And they just drew the average line. Now there's another correlation of permeability with saturation. And you can see that the higher the water saturation is, the lower the permeability. What does that mean? What does that tell you in terms of your intuition? Who would like to help me with that? Sorry? Louder. Why is permeability an inverse function of saturation, of water saturation? Now that you have the question, you don't have the answer. Okay, good. Anybody else? Okay, help me out with that. Explain it. But why? Sorry? Okay, but a rock made up of much smaller pores, is it going to hold more water than a rock made up of large pores? Sorry? Correct, but these are all sedimentary rocks, so we'll assume they're water wet. Right, and? And? Yeah, so it's going to like water more, and it's never going to come out, right? So that's what they're trying to correlate here. Good. It's like 311 revisited, right? Okay. And then our good friend Archie, he came up with two things that are called laws or relations. And in this case, he plotted what's called the formation factor, which is RO over RW. And here he plotted it again. Sorry, my brain's thinking permeability. And this, of course, is permeability. This is porosity. Okay. What do you think? Did he get it right? If you take this group of points, you can draw a line through it and so on. That looks pretty good. Similarly, that looks pretty good. Pretty good. Pretty good. Pretty good. So one could conclude that in fact, porosity is governed by, resistivity is governed by porosity. We're not solving for porosity, we're measuring resistivity. So this relationship that we're seeing given to us from Archie appears to be competent. Now, what about the permeability model? Well, the permeability model says that the formation factor is related to the inverse of permeability. Now, for those of you who had me for Petty 311, be quiet for a minute and let's pick on someone who didn't. Who wants to volunteer? Should permeability be correlated with the resistivity factor? Any ideas? Somebody volunteer. Sorry? Okay.
I would say yes, because you can relate resistivity to porosity and somehow porosity.
Okay, now you've jumped to the end of the story. That's exactly correct. That there is no unique relationship between permeability and resistivity. The relationship is between permeability and porosity. These were unconsolidated, lightly consolidated sandstone samples, so the relationship between porosity and permeability is what governed the relationship between the formation factor and permeability. In simple terms, if the plots on the right-hand side had been validated by theory, then we would be able to evaluate permeability using well logs. And we know we cannot do that, except in cases where the porosity and permeability are correlated. Now, we can try to take multiple well log responses and correlate that with permeability. That's been pretty active the last 25, 30 years. The ability to use computers for matching that is pretty good. I dare say I don't want to use this word, but a neural network is probably what the commercial software are using that you'll see there. And the only thing I know for sure about a neural network is they're wrong, so I wouldn't rely on that. I'm going to jump through these, and you can come back and take a peek because the homework will include this. And we're going to talk now about small-scale heterogeneities. How far is 5 centimeters? It's 2 inches. Okay, so this is approximately 4 inches, standard core. And then how long would this be? That's about 4, 8, 12, something like that. So this is a very small piece of core, about like that. How many different layers does it have? What's 26 minus 1? 25. Because it starts at A and then ends at Y. What's the trick? Why is it a trick? Because there's actually, well, I won't make a big deal out of it. What's the lowest permeability on this graph? Does anybody see it? The highest is 310, right? What's the lowest? 1.5. So what everybody's saying right there? Is that right? Bilhan? The lowest permeability is right here. They're indicating it's 0. But we won't worry about that. And the average permeability from that plug was 17 millidarcies. So you've got 26 layers over 15 inches, a range in permeability from 300 to 0. Somebody tell me what this piece of rock is going to act like in the reservoir. Think carefully. Had a phone call this morning from our friend. Their company starts with X E and has X's in the middle. Their number one problem in gas well development is they're looking at multiple layers, 25 to 50 layers of penetration. Now that's a much larger scale. They're looking at layers on the order of feet. We're looking at 1 foot plus with 26 layers, 25 layers. How do you think this piece of rock is going to flow? Is it going to be good, bad? Don't know. Is it going to matter if it's transient or pseudo-steady state? Is that small scale flow barrier going to be a flow barrier? Yes? Maybe? Okay. This is the Roetglins sandstone. It is aeolian. What does aeolian mean? It's wind deposited. So these dunes that form the sandstone repeat over and over again. They're on the order of maybe a few tens of meters. I looked at a case earlier, it was last year now, of another reservoir in Latin America that was also an aeolian system, and it had multiple dune sequences. They could map these. That's what they pay geologists for. And they were drilling horizontal wells in them. And that was not a good idea because they had very significant flow barriers between the dune facies. So that was one case in a million where horizontal drilling is probably not as good as vertical. Now, these are measurements that we took at the field scale. This is permeability estimated from production data, which is decline type curve analysis, and from pressure transient test. And I can assure you we did the best we could. These are permeabilities taken from where? From Core Lab. This is 1 over 1,000. This is 1 over 100. This is 1 over 10. What's going on here? The one thing you notice for absolute certainty is that the permeabilities measured in the field are substantially lower than the permeabilities measured in the laboratory. And in the laboratory, we took a distribution, we fitted a distribution, and we picked the median value. So this is some biasing there. What happens out in the reservoir when you're testing it? It samples everything. And of course, unfortunately, the permeabilities in the laboratory are dry air, so that's automatically a factor of 10 too high. But what's really going on here? If you look at this particular trace, you can see the permeability is changing. This is a logarithmic scale. It's changing 4 orders of magnitude. Okay? And then we're going to come in and we're going to say that the average permeability for this, I don't know, is right here. I'm just making this up. I don't know. So it is virtually impossible to try to scale something that you see in the core with something that you see in the field. The biggest reason is the piece of core is that big. How big is the block of rock you are sampling during the pressure transient test? Anyone? Is it as big as this room? Much bigger. Is it as big as this building? Depending on how long you test, it's probably at least as big as the building. Is it as big as this block? Possibly. Permeability is high enough. Your test is designed well enough. You could test a tremendously large volume. And because of the way we treat flow and porous media and we reverse calculate or use a model to estimate properties, the behavior that we see coming out of the reservoir matches the model. You won't doubt that by the end of this course. But when you calculate a permeability of 1 millidarcy at reservoir conditions from a well test or from production data, and you calculate a permeability of 50 millidarcies from core data, what's that tell you? I gave a presentation once where somebody, a geologist, stood up and said, "They're not related, dummy." And he's right. You just incorporated 5 or 6 scales. You went from core scale, which you can hold in your hand, to reservoir scale, which is at least the size of the building and probably the size of this block, or at least a good portion of it. So why take core data? Why take well test? Johan, you want to play devil's advocate and tell them why they're going to do these things? Because the only thing you can ever trust is a measurement made at the scale of interest. If your scale of interest is the core, do the best damn measurement you can. If your scale of interest is the reservoir, then do the best you can. These are not supposed to agree because the features that we're seeing at core scale are so small, it may not be possible for us to scale that up. I know it's time for the thingy, but somebody tell me, if you were going to devote your life to trying to resolve this, how would you start? Anybody?
Relate the core sample size
to reservoir size. No idea? Sorry? Okay. You could take an infinite amount of core. And this is the best way I can explain this. We're looking at this scale for our core, and we're looking at this scale for well test, pressure transient test, or production analysis. Okay? Now, the actual reservoir looks like this. The reservoir engineer, his model or her model, looks like this. So that model is not going to capture small scale features, is it? This ought to make you real uncomfortable. It ought to make you mad, in fact. Because we're going to ask for information at multiple scales. But in the end, we're going to model this thing probably based on a pretty big set of assumptions, like an average porosity and an average permeability, etc. And this works about 95% of the time. When is it not going to work? Anybody? Okay, so you're saying that if this segment let me find something, is low permeability, then a molecule of fluid may decide to go that way around it. Okay? And that's a cartoon-like explanation of what you said, but that's exactly right. That when we see features that have a great deal of contrast, that's when the block model fails. Okay? How many of you think I'm talking about reservoir simulation? I'm not talking about the reservoir simulation you're going to learn in the course that you're going to take next year. I'm talking about modeling something with a relatively simple concept. Now, when I go to reservoir simulation, I include all the detail at the scales that I think I can break this down into. So I'll model this as a block, this is a block, this is a block, this is a block, and so on. Bilhan? That's pretty clever, huh? I can take geophysical information and I can sort of make a diagram using a geologist, split it up spatially. Somebody tell me how I'm going to assign a porosity and permeability of those blocks. You guess. And then how do you validate your guess? Yeah, but you have no well log there. I'm talking about the rest of the reservoir at which the well is not connected to. You cannot take measurements. So how do you do it? Okay, so you come up with some special technique for guessing the permeability of things you don't know and the porosity. What's that guessing technique called? It's called geostatistics. You have a course on that next year. Okay. Then how do you validate your guesses? Sorry? Production data. Okay, so you compare the model that you have populated with guesses to the actual performance. Okay, so how many guesses did you make? Let's say 1,000. And how many pieces of data do you have to compare to it? A few dozen. Have you ever tried to use Microsoft Solver when you have more parameters than you have data? It doesn't work. So you have to come up with a whole new science of how to solve problems with more variables than you have equations or data to connect them to. Okay, time for the quiz. Everything off your desk.